Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to talk about some ligands which are based on phosphorus in the oxidation state 3. So, we talk about it as phosphorus 3 ligands. In many instances, organometallic chemistry is associated with a metal carbon bond, and that is correct, but you also need some other ligands to support the metal carbon chemistry that is going on. So, in general, there are a variety of ligands which are useful in organometallic chemistry. The most common ligands, of course, are the ones which have the carbon metal bond, and that can be carbon monoxide, which is what we have already discussed. We can also talk about carbene ligands and carbine ligands, which are all having a single carbon attached to the metal center. On the other hand, there are several ancillary ligands which also support organometallic chemistry, and these do not have a metal carbon bond. And today we are going to talk about one such ligand, and that is the phosphorus 3 chemistry. Metal hydride chemistry, metal nitrosyls, metal dinitrogen chemistry and metal halides are all important in organometallic chemistry. Although the chemistry may not happen at the metal carbon center, these are good supporting ligands. So, I am calling it as those ligands that support organometallics. So, today we will talk about phosphorus 3 ligands. There are some distinct advantages to phosphorus 3 ligands, and we will consider them one by one. First of all, it is a good sigma donating ligand. Because phosphorus is in the oxidation state 3, a pair of electrons on phosphorus can be donated to the metal, and the phosphorus 3 ligands can be varied extensively, contrary to carbon monoxide, where carbon monoxide cannot be changed. You can only change the oxygen to sulfur or to selenium. But in the case of P3 ligands, you can change the R group which is attached to the phosphorus extensively. So, you can react this molecule PX3, usually it is the halogen, which is usually, if X stands for a halogen, you can change the halogen to an R group using a reaction with the Grignard reagent and make PR3 molecules. Now, these PR3 molecules can also be varied. You can change the R group to R1, R2, R3, and this synthesis is relatively easy. So, because it can be done in a stepwise fashion. The other great advantage of phosphorus 3 ligands is the fact that X-ray crystallography of especially PPH3 complexes becomes very easy because of some supramolecular interactions that are there in triphenyl phosphine. And so, whenever you have PPH3 as an ancillary ligand, the organometallic complex is easy to crystallize, and if it crystallizes as a single crystal, one can do the crystallography of this molecule and study the solid state structure very readily and extremely accurately. One can also carry out phosphorus 31 NMR spectroscopy, and this is again a very useful technique, because no other element in the molecule might interfere in this spectrum, and only the ligand is visible in the NMR spectrum. So, this becomes an extremely useful tool because of non-interference, and only the active species is visible. Infrared spectroscopy is unfortunately of not much value in this instance, because the metal phosphorus bonds, these single bonds are possible, it is possible to observe them in the infrared spectrum, in the very low energy regions like 300 to 400 centimeter minus 1. And because this region 300 to 400 is quite crowded, it is very often not useful as a tool to analyze the phosphorus 3 organometallic chemistry that goes on. Let me say a few words about 31P NMR. It is an extremely useful technique, but unfortunately it is an empirical tool. And when you call it an empirical tool, it only means that it is based on prior evidence that you have, and you can in fact use this empirical tool based on prior evidence. If you have a crystallographically characterized molecule, one can use the 31P NMR usefully, because one assumes that the solid state structure and the solution NMR have to be related. Coordination to the metal usually shifts the ligand signals upfield. Now, this is what happens. The coordination of the metal shifts the ligand signals upfield, but the 31P signals can also be shifted downfield by up to 30 ppm. The usefulness of this tool is significantly affected because of this empirical nature and the fact that the signals are in unusual regions with respect to the free ligands. There is another erratic behavior of phosphorus 31 signals, and that is the fact that if you have a chelated molecule. So, let me write down chelate, an example of a chelate molecule. If you have bis diphenyl phosphinoethane, which is this ligand. Now, this ligand is now capable of coordinating to the metal through 2 phosphorus centers, and so a chelate ring will be formed. Depending on the chelate ring, in this particular case, what I have written is a 5-membered ring, 1, 2, 3, 4 and 5. This 5-membered ring is formed, and then the shift can be at plus 20 ppm. Whereas, if you have a single carbon, then the shift is minus 20 ppm. So, because of this erratic behavior of the chemical shift, sometimes it becomes difficult to interpret the NMR spectrum of this phosphorus metal complexes. But otherwise, if you have prior knowledge about the way the chemical shift changes on chelation, it turns out to be an extremely useful tool. Okay. Based on based on the information that we have so far, we can see that phosphorus 3 ligands can be readily synthesized, and they can be synthesized in a variety of R groups, having a variety of R groups. Now, the question arises, what kind of a ligand is this PR3? The PR3 group, is it a good donor? Is it a good sigma donor, or is it a pi donor? One can also ask the question, is it a pi acceptor? If you look at the complexes formed by triphenylphosphine or trialkyl phosphines, then one can understand, based on the structure and the spectroscopy that we do, we can figure out what kind of a donor we are dealing with. So, let us take a look at a little bit of the chemistry that is there in this molecules. First, let me give you an example of how one can synthesize this triphenylphosphine complexes, and that will illustrate the chemistry that I am talking about. Let us take a molybdenum hexacarbonyl complex. This is a molybdenum hexacarbonyl complex. I treat that with 2 equivalents of triphenylphosphine. This appears to be a general way of synthesizing phosphorus containing molecules. You can take any labile ligand. In this particular case, carbon monoxide turns out to be useful, because carbon monoxide will escape into the reaction medium, away from the reaction medium, and you will be left with the complex. You would expect the treatment of MoCO6 with 2 equivalents of triphenylphosphine will result in the formation of a trans complex, or it can result in the formation of a cis complex. It turns out that exclusively the cis octahedral complex is formed. Only the cis octahedral complex is isolated from this reaction mixture. if you look at the complex itself, you can very easily see that carbon monoxide has no great steric influence. It is only the phosphorus containing ligand which has got some steric influence. So, if you want to pack two ligands, two phosphorus containing ligands around the molybdenum, it would be best to have the trans geometry, because the two L groups are far away from each other. But surprisingly, it is the cis ligand which is cis complex which is formed and the trans complex is not formed. So, there must be an electronic reason for this particular preference. Very often, it is good to form a particular opinion by looking at a variety of complexes. So, this has been done in the case of phosphine complexes. Both trans and cis have been attempted, preparations of these have been attempted, and almost always the cis complex is what is observed in many metals, and with many carbon monoxide geometries, one forms only the cis complex. Now, one can also make the tris coordinated complex. The tris trialkyl phosphine complexes have been synthesized, and here again you can have two particular geometries. One is called the Mer geometry, where the three ligands are placed in a meridional plane. The three ligands are placed in a meridional plane. Then it is called a Mer complex, and then you can also have a Fac complex, and the Fac complex you have a facial geometry. So, one face of the octahedron is occupied by the three ligands, which are the phosphorus 3 ligands. So, between these two geometries, you will notice that the Fac complex always has one L trans to a carbon monoxide. Always you have one carbon monoxide trans to an L group. So, all three L groups have got a trans carbon monoxide. You will notice that each of these L groups has got a trans carbon monoxide, whereas in the meridional geometry, you do not have that particular situation. In one case, which is this particular L group, you do have a trans carbon monoxide, but the other two L groups do not have a carbon monoxide opposite them. Now, it turns out that you can distinguish these two species very easily using the carbon monoxide stretching frequency, because that depends on the trans ligand. So, based on carbon monoxide stretching frequency, you can find out that it is only the Fac isomer which is formed and the Mer isomer is not formed. So, we have two situations now, both in the di-substituted case and in the tri-substituted case. We can see a clear preference for the ligand L to be trans to a carbon monoxide, and this electronic preference needs to be explained in order for us to understand why exactly L prefers this geometry and what is the electronic reason for the same. Okay. So, let us now look at the traditional explanation which was available until the mid 1980s. People normally gave this explanation, and we will discuss this first because it illustrates an important scientific principle. Whenever there is a argument or a discussion regarding a concept, one achieves a better explanation at the end of the discussion. So, here is an explanation that was given. Originally, people thought that PR3 groups are pi acceptors, and this pi accepting property arose from the 3d orbital which is empty, because the phosphorus is a element which has got the valence electrons in the 3s and 3p. So, remember 3s and 3p are the valence electrons, and these are the ones which are having the 5 electrons which are there on phosphorus, and the 3d is usually empty. So, because the 3d is empty, people thought that the acceptor strength of the PR3 group comes from the 3d orbitals, and they have the right symmetry to overlap with metal orbitals. So, let us take a look at what we are discussing here. Here is the molybdenum center interacting with the phosphorus 3 molecule. The 3 molecules, the 3 arms of the phosphorus where the R groups are present will be distributed just like ammonia in an umbrella like fashion, and the lone pair on the phosphorus is now pointed towards the metal atom. It has got 2 electrons, and this lone pair is going to be donated to the metal. So, this is the electron density flow in the sigma orbital that we are talking about. And if the phosphorus atom has got a 3d orbital, it has got a 3d orbital, then the 3d orbital can interact with the metal's 3d orbital, and if this is empty and if this is filled, so you have a filled metal orbital and you have an empty p orbital, phosphorus orbital, which is a 3d system, then you can have electron density flowing in this direction. So, this kind of an electron density flow will result in a pi acceptor behavior. So, people thought that phosphorus ligands are good pi acceptors because of this electron density flow going from the metal d orbital into the empty d orbital on the phosphorus. So, how does this help us to explain the geometrical preferences that we observed earlier? Because carbon monoxide is an excellent pi acceptor, carbon monoxide is one of the best pi acceptors that we know. Because this is the best pi acceptor that we know, it is natural that carbon monoxide would like to have a poor pi acceptor in the trans position. Now, you might ask, why is this the situation? Why should it be in the trans position? And that is because this d orbital that is there on the molybdenum center, this is the d orbital that is there on the molybdenum center. I have drawn it slightly pushed away from the center, so that you can understand the overlaps. You can see that the d orbital that is involved in this d pi interaction, this interaction that we are talking about, is on the same axis as this carbon monoxide in the trans position, and it is the same orbital which will have to donate electron density in both directions. It will have to donate electron density from the metal d to the phosphorus d. It will have to give electron density from the metal d to the pi star of the carbon monoxide. So, this is the interaction that we are talking about. There is a competition between the phosphorus empty d and the carbon monoxide pi star. This is the pi star, and you can draw the second set of orbitals also. This would be shaded and this would be empty. So, this is the pi star orbital, and the electron density has to flow into the pi star of the carbon monoxide, and that is what usually one observes in all the complexes. So, because carbon monoxide is such a good pi acceptor, the phosphorus is a poorer pi acceptor. So, by putting 3 phosphorus ligands trans to carbon monoxide, the carbon monoxide ligands are kept happy, because they will have enough electron density moving in this direction. Whereas, if you have the phosphorus ligands all in the meridional position or in the trans position, you will notice that the carbon monoxides also have to be trans. If the carbon monoxide is trans, one carbon monoxide competes with another carbon monoxide for the same d orbital, and that is an unhappy situation for the metal. And so, it does not prefer that situation, and it likes to have a phosphorus which is a poor pi acceptor opposite carbon monoxide, which is a strong pi acceptor. Now, how do we know that whatever we have said so far is true? If you look at carbon monoxide stretching frequencies in the FAC complexes, here is a FAC complex that I have that we are talking about. This is a FAC complex because the 3 ligands, the substituents are in the facial position of an octahedron, and then the carbon monoxides are on the opposite face. You can look at the symmetric stretching. This is the symmetric stretching and the antisymmetric stretching of the carbon monoxide, and you will find that if you have a very good donor on the face, or on this face, for example, if you have a very good donor, then the carbon monoxide stretching frequency reduces quite significantly. You will notice that in MoCO6, that is in molybdenum hexacarbonyls, where carbon monoxide is trans to another carbon monoxide always. So, this is the observation for MoCO6. Then you have a stretching frequency of 2004 centimeter minus 1. Adding a ligand like di-N, which has got 3 nitrogen donors in the facial position, results in a very low stretching frequency for the carbon monoxide ligands. That is because electron density flows from the nitrogen to the metal and from the metal to the carbon monoxide very effectively, and so the stretching frequency goes down. The moment you start adding a ligand which can compete with the carbon monoxide for electron density, then the frequency of the carbon monoxide slowly keeps going up. When you have triethyl phosphite, for example, in this case it is POET thrice. If you have POET thrice, then the triethyl phosphate happens to be a better pi acceptor than triethyl phosphate. So, triethyl phosphine PET3. So, this is a poor pi acceptor. It's a poor pi acceptor. This is a good pi acceptor. So, if you have a good pi acceptor trans to the carbon monoxide, then the stretching frequency is higher. So, you can see that as the stretching frequency of the 3 carbonyl ligands go up, you can see that the electron density on the metal has gone down, because the phosphorus atom is also competing for the electron density. So, that is the reason why you have this competition between the d pi interaction between the phosphorus and the metal, and the d pi star interaction on the carbon monoxide. These two compete with one another, and so it is better to have the phosphorus ligands in the trans position. One can look at this graphically to understand it and appreciate it better. Here is an example where you have the 3 carbon monoxide ligands having 2 stretches, a symmetric stretch and an asymmetric stretch. Both of them are plotted in a series, and you find that the metal carbonyl complex, the pure metal carbonyl complex, which is marked here as MoCO6, has got the highest stretching frequency, but you put good donors on the trans position. The best donor, that is the nitrogen donor, has a very low stretching frequency, but as you increase the pi accepting nature of the phosphorus ligand, the stretching frequency keeps increasing. So, the electron donating power of the trans ligand keeps increasing in this direction, and the trans carbon monoxide stretching frequency keeps increasing in the opposite direction. So, this is a very clear indication of the fact that the trans ligand competes for the same d orbital for d electron density for pi donations. So, this explanation, this traditional explanation was quite satisfactory, and it was used in the textbooks for a very long time, but in more recent textbooks you might find it that it is being disputed, because people found by computational methods that 3d orbitals are actually not available or accessible for the metal d orbitals. So, the metal d orbitals are in one particular energy level, and the 3d orbitals are much higher in energy. So, if one has to represent this graphically, one can say that these are the metal d orbitals, and the phosphorus d orbitals are much higher in energy. So, the interaction between these 2 orbitals will be very poor, because the energy matching is important for forming bonding and anti-bonding molecular orbital. So, because of this controversy, people have abandoned this explanation that the d orbitals on phosphorus are actually involved in d pi interactions. So, this gap that is large has resulted in abandoning of this explanation, and one also notes the fact that you cannot measure the energy of empty orbitals, and so it is difficult to disprove or prove this particular point that we are talking about. As a result, there was an alternative explanation that was built around what is called a sigma only theory. That means, phosphorus ligands are only good sigma donors and there is no pi interaction that is present. So, this particular theory was able to explain a few of the observations that were present. Let us just take a look at some of the explanations that could be made using the sigma only theory or the no pi bond theory. The decrease in the nu CO is proportional to the electron density on the metal atom. If the py3 ligand is a good donor, then metal has got greater electron density. If the metal has greater electron density, CO has less stretching frequency because the pi star orbitals are populated to a better extent. If py3 is a weak or it is a weak sigma donor, then the nu CO is higher. This explanation also seemed to be reasonably sufficient, because the type of electron donation that we are talking about is an electron donation from the 3sp hybrid on the phosphorus to the metal. This is the d, if this is x and this is y, this is dx squared minus y squared, accepts electron density from the phosphorus, and it is the dxz on the phosphorus on the metal which is interacting with the pi star on the carbon monoxide. So, this type of an interaction would be sufficient to explain the type of electron density changes that are happening on the carbon monoxide and also subsequently the carbon monoxide stretching frequencies. One way in which people try to explain these changes is to look at the ionization potential of the phosphorus atom. Because the electron density that is being donated from the phosphorus is on the hybrid orbital, the lone pair on the phosphorus, if you do ionization of the phosphine, the electron is coming out from the phosphorus hybrid orbital. So, the extent to which the phosphorus is able to donate a pair of electrons to the metal must depend on the ionization potential. If the ionization potential is low, then this is a good donor. If the ionization potential is very poor, as in the case of PF3, this would be a poor donor. So, as you increase the ionization potential, the donor ability of the phosphorus will come down. A second way to look at this is to also look at the ligand and the pKa, which means the easiness with which you can remove a proton from the protonated phosphine. So, the extent to which you can give the electron density on the phosphorus to the proton is dependent on this particular equation. This is obviously an equilibrium, and if you have a very high value of pKa, then that means that the proton is not easily dissociated, and so that means that this is a good donor of electron density. If you have a very small value, as in the case of PPH2 OMe, then this is a poor electron donor. So, this can also be correlated with the stretching frequencies, and it was indeed possible to analyze the type of changes that you have with electron density donation from the phosphine to the metal and the frequency changes that are there in FAC complexes. So, this explains all the observed results from the infrared stretching frequencies, and one could almost confidently say that there were no pi effects in the interaction of px3 with a metal atom. So, px3 is a sigma donor and there is no pi interaction at all. However, it is possible for us to explain the stretching frequencies, but not the bond distances. In fact, if you look at the bond distances that are there between phosphorus and the metal, one can see that one can expect longer phosphorus metal bonds due to poor phosphorus to metal bonding in the sigma manifold. So, if you have electron donation from the phosphorus to the metal, if you have a poor sigma donor, you should have longer bonds. If you have strong sigma donation, you should expect stronger or shorter bonds. But this is what you expect, but what is observed is something else. Here is where the no pi bond theory fails. Let us take two examples. One example is the case of PPH3 with CrCO5. Here we have a mono-substituted carbonyl complex. So, you have CrCO6 where only one phosphorus ligand has been added, and you can also compare it with the triphenyl phosphite complex, which is given here. And we can now look at the phosphorus chromium bond distances that are there in these metal complexes. Suppose you have a PCR distance of 2.422 angstroms in the case of the triphenyl phosphine complex, and this is an instance where the POPH complex will have less electron density to donate. So, you would expect a longer bond distance for this particular complex, where you have a weak donor. So, POPH thrice is a weak donor. This is a weak donor and this is a better donor. So, the better donor should have the shorter distance, but we find that this is exactly the opposite of what you would expect, and you have a shorter bond distance for the triphenyl phosphite complex. What is interesting is that you would expect, for the same reasons that we have discussed, if you have good sigma donation, the trans carbonyl should have the longer bond distance. But this is also in the opposite direction. So, it is very clear that the no pi bond theory or the sigma bond only theory is not sufficient to explain all the data that we have in terms of crystallography. So, you expect something else other than the sigma bonds to explain these bonding interactions. One of course knows that POPH3, if because it is a better electron withdrawing group, this would form better pi bonds between the phosphorus and the chromium. And if this forms better bonds between phosphorus and chromium, the pi bonding is there, then this is exactly what one would expect. The phosphorus chromium bonding would be short, and the phosphorus chromium bonding in this case, where there is poorer pi interaction, would be longer. So, the pi bond theory is able to explain the bond distance changes in these cases, whereas the sigma bond only theory is not able to explain these changes. I will give you one more example where this has been conclusively shown, and I take an example where the two phosphorus metal distances are in the same complex. This is always a good way to make comparisons, because there are many factors that go into a metal ligand bond distance. So, here is a case where you have PPH2, which is a good electron donor, compared to PCF3. CF3 is an electron withdrawing group. So, this would be a poor donor and better acceptor. This is a good donor relative to this phosphorus, one can see that this phosphorus is a better donor. And if this is a better donor, one would have expected, based on sigma bond only theory, this should have a short distance, whereas we find that this distance is longer. So, clearly there are some pi effects in the explain that need to be used in order to explain the short bond distance that is observed. 2.17 for this phosphorus platinum bond, and this bond distance is 2.24 angstroms. So, one can explain these bond distance changes using the pi effects, because this is a better pi acceptor. You have multiple bonding between the phosphorus and the platinum, you have multiple bonding, and so this bond distance is reduced from what you expect. A similar explanation can be offered for these complexes. When you put two triphenyl phosphines trans to each other, you are competing for the same d orbital electron density. When you have a chloride trans to a triphenyl phosphine, then you have a pi donor trans to the triphenyl phosphine. And if there is a pi effect, then the electron density can flow from the chlorine to the rhodium and from the rhodium to the triphenyl phosphine. So, because the pi bonding is reinforced, the pi bond in the phosphorus trans to the chlorine is reinforced by electron density being donated from the chlorine to the rhodium and from the rhodium to the phosphorus. This pi bond is in fact making this bond distance shorter. It is 2.22 angstroms, about 0.1 angstroms less than what you expect for this triphenyl phosphine, which is in this complex. So, you have a same complex, two complexes that are being compared. In both complexes, you compare the bond distances within them. We are not comparing the 2.24 here with the 2.32 here. Rather, we compare it within this system. Within the platinum complex, you compare two phosphorus platinum distances, and within the rhodium complex, you compare this phosphorus rhodium distance with the rhodium phosphorus distance, which is there along this direction. Okay. So, the pi bond theory is able to explain why the triphenyl phosphite has got a short distance 2.309 versus the triphenyl phosphine, which has got the longer distance, and that is because of the pi bond which is there between the phosphorus and chromium, which is more effective in the case of the electron withdrawing phosphite, which is present here. Now, if we cannot explain the pi bonding using the d orbitals, how can we explain the pi bonding? To do this, the computational chemists came up with the idea that you can have what is called negative hyperconjugation. Negative hyperconjugation or donation of metals filled d orbitals to the sigma star orbitals of the px group. So, if you have a px bond and the px will have a sigma bond or a sigma orbital corresponding to the sigma bond and a sigma star orbital, and if this sigma star orbital on the phosphorus is capable of accepting electron density, then one can say that there is negative hyperconjugation from the metal to the phosphorus px sigma star. Now, can these px sigma star orbitals accept electron density? Can they accept electron density, and if so, what is their shape and symmetry? So, depending on the shape and symmetry, you can expect them to behave as good pi acceptors. So, this is what we are going to see in the next section. Here I have for you the molecular orbitals of a hypothetical phosphine, which is pH3, which is arranged according to the energy. If you look at the three sigma bonds or the pH sigma bonds, they form a set of molecular orbitals, bonding molecular orbitals. So, all of these are filled. These are filled molecular orbitals. These are filled molecular orbitals, And then we have the traditional lone pair, which is sitting on the phosphorus, which is pointed away from the 3 groups which are there on the phosphorus. So, this is, if you want to talk about the metal interacting with the phosphorus, then this would be the direction in which we are orienting the phosphorus ligand. So, the phosphorus has got a large lone pair, which is sitting on the face opposite the 3 hydrogens, and it is pointed in such a way that it can be now donated to the metal atom. That is your sigma bond between the phosphorus and the metal. Now, the pi acceptor orbitals are actually coming from the sigma star orbitals, which is the sigma star orbitals of the pH bonds. The sigma star orbitals are primarily phosphorus px and py. If this is the z axis, if this is my z axis, then the px and the py, x and y, this px and py orbitals are what you see here. This is my px and this is the perpendicular py direction. So, the px and the py orbitals are the empty orbitals. These are empty and they can accept electron density. So, this is how the phosphorus atom is able to accept electron density from the metal. From the metal, electron density flows into the sigma star orbitals of the phosphorus x bond. The px sigma star is capable of accepting electron density. It turns out that it has the same shape and the right symmetry to overlap with the metal orbital. So, phosphorus is a good pi acceptor, not because of the empty d orbital, but because you have the sigma star orbital, and that sigma star orbital has got greater contribution from the phosphorus, and it is primarily the p orbitals which are present on phosphorus, which contribute maximum to the sigma star orbital, and so it is able to accept electron density from the filled orbital of the metal. Arsenic X3, arsenic Y3 and antimony Y3 groups should also be good, as they are also less electronegative than R groups, and so they have a good option of accepting electron density into the sigma star orbitals. Now, one can also ask the question, why is it that amines or NR3 groups are not good pi acceptors? This is surprising, because in the periodic table, we find in the same group NR3 is only a sigma donor. These are only sigma donors and not pi acceptors. One can in fact categorically say that these are not pi acceptors. So, why is it that they are good sigma donors and not pi acceptors? Nitrogen is in fact more electronegative than most other groups. In the case of ammonia, for example, it is definitely more electronegative. Nitrogen is more electronegative than hydrogen, and so nitrogen has got good contribution to the bonding molecular orbital, but the sigma star has most of the contribution from hydrogen. I will show you the molecular orbitals of NH3 as an example. Here you can see that the nitrogen contribution to the bonding molecular orbitals are significant. These are all filled now. You have filled molecular orbitals here, and this is the lone pair, and so that again is a good donor orbital. But you can see that the sigma star orbitals, where you have these 3 sigma star orbitals, these are the sigma star orbitals, you can see that the contribution of hydrogen is significantly greater compared to what you had in the case of triphenyl or trialkyl phosphanes, where phosphorus, because of its lesser electronegativity compared to nitrogen, contributes more to the sigma star orbital. So, one can say that the electronegativity between A and H in AH3 is responsible for the sigma star orbital being capable of accepting electron density. If A is less electronegative, then A will be a good sigma star pi accepting ligand. So, in the case of phosphorus, arsenic and antimony, they are good sigma star orbitals capable of accepting electron density. Now, we can go back to this figure and see if the pi donation to the sigma star orbitals are capable of explaining the carbon monoxide stretching frequencies that you have observed. First, let us take a look at what we saw earlier. If you have OET groups which are strongly electron withdrawing, we find that the frequency of the trans carbon monoxide is in fact higher. So, the frequency is in fact increasing in this direction. When the group was a phenyl group, then it was not as good a pi acceptor, but when we have OET, it is a very good pi acceptor. And so, you find that relative to MoCO6, which was listed here, the OET has got the trans carbon monoxide stretching frequencies closest to MoCO6. So, POET thrice is a very good pi accepting ligand. So, POET thrice is a very good pi accepting ligand. So, let us now go forward and we see that suppose we had chlorine and phosphorus. In the previous diagram, we did not have the PCl3 and the PF3 ligands. Suppose we add the PCl3 and the PF3 ligands, we find that these complexes have got stretching frequencies which are even higher than what you expect for PR3 groups. So, here you go, MoCO6 had this stretching frequency at 2004 centimeter minus 1, and in the case of PCl3 and PF3, the stretching frequencies are even higher. They are at 2040 and 2090 centimeter minus 1. So, clearly you have a situation where the trans ligand is capable of attracting pi electron density as much as carbon monoxide. PCl3 and PF3 are able to compete with the trans carbon monoxide for pi electron density, and so the trans carbon monoxide stretching frequency has increased beyond what you have for MoCO6. So, this explanation is again something that could not have been given by the sigma only theory. So, in FAC compounds, carbon monoxide is competing against a poor pi acceptor, and that is why it is a situation which leads to greater stability, and so FAC compounds are more stable than MER isomers. And it is also true that the carbon monoxide stretching frequency is changing in the way in which it changes for a series of complexes based on the trans ligand. The trends are reversed in the case of PCl3 and PF3. So, when you have PCl3 and PF3, you have a situation where the trans carbon monoxide has greater stretching frequencies than MoCO6, where the trans ligand is carbon monoxide. Now, based on these factors, Tolman in fact devised what is called Tolman's electronic parameter. Tolman's electronic parameter measures the extent to which the complex NiCO3L has two stretching frequencies for the system which is pictured here. So, the reason for choosing this nickel complex is the fact that you can readily make it by reacting NiCO4. You can react NiCO4 with any ligand and it will readily form NiCO3L, and you can readily measure the infrared spectrum, and you can see that as you substitute a good carbon monoxide with a phosphorus ligand, the stretching frequency of the trans carbon monoxides are lower than what you expect for NiCO4. But as you substitute the trans ligand, you tend to have an increase in the stretching frequency. So much so that in the case of PF3, the stretching frequency is close to that of free carbon monoxide. In other words, there is very little pi star electron density on the carbon monoxide. When you substitute the ligand with L equals PF3, there is very little electron density that flows into the carbon monoxide ligands, the pi star orbital, and so the stretching frequency is close to what you expect for free carbon monoxide. So, this is the reason why you end up with a good pi acceptor in the trans position is always competing for the carbon monoxide electron density, and so you have poor pi acceptors in the trans positions. And if you have a good pi acceptor like PF3, then the stretching frequency of carbon monoxide is close to the free carbon monoxide stretching frequency. So, pi fx alone may not be sufficient to explain many of the interactions that we have described. The charge induced on the metal also plays a role, and this is something which we have not discussed in this lecture, but we will discuss it in a lecture on carbon monoxide. And one should also remember that bonding is dependent on steric effects. This is again a factor which we will explain in a future lecture. Now, discussed so far, what we are going to do is to look at a diagram which will tell us what we have discussed so far in a diagrammatic fashion. We first looked at phosphorus ligands and we looked at P3 ligands and how it is easy to synthesize P3 ligands, and because we can make this in a stepwise fashion, we are able to make PR2X, PRX2 and PR3, and because stepwise formation is possible, we can make ligands which have got 3 different ligands or 3 different R groups on the phosphorus. This is a very useful tool, because if 3 R groups are present, the phosphorus becomes a chiral species. After we looked at synthesis of phosphorus 3 ligands, we also looked at how one can make phosphorus 3 complexes, and this is done by a simple substitution reaction. And having looked at these complexes, we looked at some of the spectroscopic factors that are useful in these systems. One noted the fact that phosphorus 31 NMR is extremely useful, although it is an empirical tool. Because phosphorus 31 signals are readily observed in these complexes, it is possible to use them effectively. And then we looked at phosphorus bonding to the metals. Initially, people thought that there was a double bond character due to the presence of d orbitals on the phosphorus, and then it was realized that it was not just the d orbitals on phosphorus. It is possible to have electron donation to the sigma star orbitals on the phosphorus due to negative hyperconjugation. And the alternative suggestion that it is electron density is flowing into the px sigma star is quite sufficient to explain all the factors which we have observed in the case of metal phosphorus bonding. Finally, we looked at characterization of phosphorus 3 ligands, and we looked at the Tolman's electronic parameter. The Tolman's electronic parameter is extremely useful to understand the type of bonding that is there between the metal and the phosphorus ligand, and in future classes we will look at Tolman's cone angle and the buried volume concept, which is also useful for explaining the phosphorus metal bonding. So, if you look at the range of complexes that are formed by phosphorus ligands interacting with metals, one finds that it is truly a remarkable range. One can use a variety of R groups, and one can use a variety of metals, and a truly amazing number of molecules can be made using phosphorus chemistry. And this turns out to be a very, very rich field which is being actively pursued even today. This is finished.